In this video we're going to look at descriptions and diagrams for bivariate data. So, Susan wishes to determine whether there is a connection between the highest and lowest share prices of various electronic shares during a 12-month period. So she's got the data from 10 different electronics companies and has collected the high price and also the low price for each of those 10 different companies' shares. And we can easily represent the data on a scatter diagram, which looks like that. Now, when we're drawing scatter diagrams, it's often helpful to mark on the diagram the point of means. So we're going to calculate the mean high value excuse me, and the mean low value and plot that point as well. So the mean of the x values is easily calculated by adding up all of the highs. So the mean of the high values is 215.7 and the mean of the y values, in other words the mean of the lows, is 120.6. So we add to the diagram the point whose coordinates are 215.7, 120.6. Now, if we look at the diagram now, we can see that the data points are quite tightly packed around a line of positive gradient, or we say that the data exhibits strong positive linear correlation. What's more, if we set up coordinate axes with the point of means as being the origin for these coordinate axes, then you can see that nearly all of the points are in the first and the third quadrants of this new coordinate system. Let's have a look at another set of data. So this set of data shows the mileages and prices of used cars of the same make and model which are for sale on a used car website. So again, we can plot the scatter diagram for the data, and we'll also include on it the mean point of means, which in this case will be the mean mileage and the mean price. So there's the scatter diagram with the red cross being the point of means. And in this case, we can see that the points are loosely packed around a line of negative gradient. And when the coordinate axes are centered on the point of means, we see that almost all of the points are in quadrants 2 and 4. We would say that this data exhibits weak negative linear correlation. So it's not, the points aren't closely packed around a line of negative gradient. They're only weakly packed around a line of negative gradient. So we're using the description weak negative linear correlation here. For our third set of data, we've got 10 students were selected at random from a year class 9, and their percentage marks in a maths and art were recorded. So again, we've calculated the mean of the maths marks and the mean of the art marks, and there's our scatter diagram of the points together with the point of means marked in red. And in this case, we can see that the data is not even loosely packed around a line. Look, depending on how you look at it, you could think about a line of positive gradient, you could think about a line of negative gradient. Certainly no clear line that describes that set of data. Looking at the points, they're pretty well spread over all 4 quadrants of the coordinate system based on the point of means. In this case here, we would say that the data exhibits no clear linear correlation. Now this next diagram shows the masses and lengths of a sample of 12 birds of the same species. Now in this case, at a first glance, it looks as if there is some positive linear correlation between the mass and the length. But if we look more carefully at the data, then we can see that there aren't any points really close to the point of means, and that the points really almost appear in two distinct clusters. Now, one wants to question what's going on when you see a graph like this, because it's possible that we might be trying to combine the results from two different distributions. For example, if the masses of the male birds and the female birds and the lengths of the male birds and the female birds are really different, then the data points of the one cluster might respond to the male birds, and the data points for the other cluster might relate to the female birds. So when you see sort of two completely distinct groups of points, be very, very careful, because sometimes it may appear that you've got some correlation when you're basically trying to merge two different populations. Now, when the scatter diagram suggests that there is strong linear correlation between the variables, then it does make sense to find out what that best fit line linking the variables actually is. And at GCSE, you'll have done the best fit line by eye. It is possible to use a calculator or a computer statistics package to find the equation of what is known as the least squares y on x regression line. In other words, that's a fancy word for the best fit line. Now in your maths for M2 and M4, you will certainly not be required to calculate the line of best fit. The equation of the line will be given if it's needed in a question. However, it may well be useful for you to know how to calculate it for your work in other subjects. And I'm thinking particularly of perhaps psychology or geography or biology, for instance. So, we're going to just spend a couple of minutes looking at how you can use your FX991 calculator to find the regression line for a set of data points. So, this stage here we're going to go back to the high-low data that we started this video with, and we're going to look at how we can set up the calculator and enter the points and determine the line of best fit. So let's see how this actually goes. Turn the calculator on and select Menu, followed by 6, followed by option 2 for y equals a plus bx. And now enter one by one the different x values that you've got. Which takes a minute or two to get through them all. We can zoom that process up here by just zooming through this little video a little bit quicker. When you get to the end of the x values, go across to the y column and up to the top. and start putting the y values in. Again, we can just zoom through that process a little bit. And then once we've got all of the values in, we need to go to the option button and tell it we want the regression calculation done, which is option 4. And there we are, we've got the regression line now is y equals a plus bx, where a is minus 4.67 and b is 0.581. So we can now record that regression line. We've got y equals minus 4.674 plus 0.5808x. So we've now added the best fit line, or the y on x regression line, onto our scatter diagram. And we should note that the regression line passes through the point of means. And that will always happen when we plot a regression line onto a scatter diagram. It will always go through the point of means. Looking at the equation of the y on x regression line, we can see the gradient of that line is 0.58, and what that means is that for each penny that the high value increases, the low value increases by approximately 0.58 pence. So we can put an interpretation on the gradient of the regression line in this context. Have a think about whether there's a meaningful interpretation of what the y-intercept of the equation has in this example. If we had another electronics share which had a high value during the year of 282 pence, then using the regression line we can predict what the low value of this share might be. So just inserting x equals 282 into the regression line, we obtain y equals 159. So we've got a predicted low price for the share of 159 pence. That's fine in this case because 282 for the high value is well within the range of x values that we've got in the sample. The lowest x value we had was somewhere around about 40, the highest x value we had was somewhere around about 350. On the other hand, if we were asked to use the line to predict the low for an electronic share that had a high of 528 pence, well, 528 pence is way outside the values of x that we've got in the observed sample, and it would not be sensible to use the line in this case for what is known as extrapolating. That is when you're trying to use the line outside the range of data values. So we shouldn't do that.